Welcome to this comprehensive guide on Time Series Spurious Regression. Have you ever noticed two things trending together and thought they were related, only to find out it was a total coincidence? In econometrics, this is a dangerous trap called spurious regression. Today, we will learn why two lines going up together doesn't always mean what you think it means. At its core, a spurious regression is a fake relationship. It occurs when two or more non-stationary time series appear to be statistically related, even though they are totally independent. This usually manifests as a very high R-squared value and highly significant t-statistics, which would lead a researcher to believe there is a causal link where none exists. To understand this, we must first define stationarity. A stationary time series is one whose statistical properties, like mean, variance, and autocorrelation, are constant over time. Think of it like a heart rate monitor. It fluctuates but stays around a stable average. Most real-world economic data, however, is non-stationary or follows a random walk. A random walk can be defined as yt equals yt minus 1 plus epsilon t. Here, the current value is just the previous value plus a random shock. Because the shocks accumulate over time, the series drifts. When we regress one random walk against another unrelated random walk, the drift in both often aligns by pure chance, creating a nonsense correlation. Let's look at a classic humorous example. If you plot the number of people who drowned by falling into a pool against the number of films Nicolas Cage appeared in over a decade, you find a shockingly high correlation. Statistically, the t-test would say they are related. Logically, we know Nick Cage's acting career does not cause swimming pool accidents. This is the essence of being spurious. The danger was formally highlighted by Granger and Newbold in 1974. They discovered that if you regress two independent random walks, the distribution of the t-statistic doesn't follow the standard student's t-distribution. Instead, it diverges, meaning that as your sample size grows, you are almost guaranteed to find a significant relationship that is actually false. How do we detect this trap? The most common tool is the Augmented Dickey-Fuller test, or ADF test. The ADF test checks for the presence of a unit root. If a series has a unit root, it is non-stationary. The null hypothesis states that the series is non-stationary. If we fail to reject the null, we must be very careful with our regression. Another red flag is the Durbin-Watson statistic. In a genuine regression, we expect the residuals to be white noise. In a spurious regression, the R-squared is often higher than the Durbin-Watson statistic, or R-squared greater than D. This is a classic rule of thumb developed by Granger and Newbold to alert researchers of potential nonsense results. So what is the solution? The first approach is differencing. If we take the change in y, or yt minus 1, we often remove the trend and make the series stationary. However, sometimes two non-stationary series are actually related in the long run. This is called cointegration. Cointegration is often explained by the drunk and his dog analogy. A drunk man walks randomly and his dog walks randomly. But if the dog is on a leash, they can't wander too far from each other. Despite their individual random paths, they move together in the long run. If two series are cointegrated, the regression is not spurious and we can use an error correction model, or ECM. In summary, always check your data for stationarity before running a regression. Don't be fooled by high R-squared values or lines going up together. Always perform an ADF test and look for cointegration to ensure your results reflect reality and not just a statistical fluke. Thank you for watching this guide on spurious regression. Understanding these concepts is the first step toward becoming a rigorous data scientist or econometrician. References: 1. Gujarati, D9, Basic Econometrics. 2. Granger, CWJ, and Newbold, 1974, Spurious Regressions in Econometrics. 3. Wooldridge, J.M., Introductory Econometrics, A Modern Approach.